Hey, how's it going, everyone? In the last video, we talked a little about the intuition behind linear regression. In this video, we'll be talking about an algorithm that powers linear regression. That is to say, that's with the help of this algorithm, linear regression finds the best fit line that captures your data, right? So if you're coming from the last video, what I mean by that is that the gradient descent tries or allows us to find the optimal values for the model parameters, right? Um, and you could have as many model parameters as you wish, right? And the gradient descent is a very efficient algorithm that will find the optimal values for all of your model parameters. But for the sake of simplicity, we're only looking at uh, the model parameter w, right? And we have fixed, in the last video, we fixed the value of b because we don't want to visualize at the moment a two-dimensional graph, right? So for the time being, we are only looking at w, right? And we have plotted the cost function with respect to w. Okay, so how do we find uh, the best possible value for w that gives us the lowest value for j, right? What we are trying to do is to minimize the cost function, right? We want to get to the very bottom here, right? So assume that w is set as some random value, right? I'll just call it randval, right? Let's call it wr, right? So this is an initial w, and let's say it happens to be that it's right here, right? It's a small value, right? It's randomly initialized, and let's say its cost is right here, right? This is the cost right here. This is j of wr. Okay, so immediately you can notice that you're very far away from the local minima, or rather global minima in this case, right? The lowest value for j, right? So the cost is huge here for initial value. So what we could do is to decrease the value of w a little bit, right? But how can we get an idea, or how does our algorithm get an idea that whether it should increase the value of w or whether it should decrease the value of w, right? For all we know, that wr could have started over here, and in this case you wanted the algorithm to actually increase the value of w to get to the global minima, not decrease it. But since we've assumed that we are starting from here, we want to decrease the value of the model parameter w. So what we can do, right, what the model, or rather our model tries to do is it tries to compute a tangent line at the point wr, right? And this tangent value is actually going to give you a slope of the line at that point, right? What that means is that if I nudge the value of w in the positive direction, let's say if I move only 1 unit, right, in the positive direction, if I increase the value of w uh, just a little bit in the positive direction, let's say by the magnitude of 1, right, how much do I increase in the direction of j, right? Let's say in this case I increase j, this looks about 1.2 or something, right? So that's the slope. We can write this slope as the partial derivative. I know this is not a derivative per se, this is a partial derivative, but just for the sake of simplicity, um, this is a derivative of the function j with respect to w, right? And more specifically, it is with respect to wr, right? Um, that is to say, it is evaluated at wr, right? This is not a right notation here. Maybe I should say you first compute the derivative with respect to w and then evaluate it at wr, right? So this is actually, this whole thing right here is actually equal to 1.2, right? But so this is the derivative. So what I wanted to do, or what we can do, because we can visualize this whole thing, we want to decrease the value of WR, right, to reach to the global minima, right? So what we can do is to subtract this term from the initial random value of WR, right? And that would actually decrease the value. Let's say this is a decreased value of WR prime. Let's say after doing this, you are here. So let's say this is equal to, we assign this to WR, and this becomes WR prime, let's say, right? But the problem with that is if the value of WR is very small, but the slope here is very large, you're going to end up with a negative number here. So you want to also control how much you want to decrease the value of WR, or rather, how much do you want to kind of jump on this curve. For example, you started over here, now you're here, right? This is a huge jump from here to here, right? So you want to be able to control this. So one way we could do that is to introduce some multiplicative factor. Let's call it alpha, right? We call this a learning rate, right? I'll just write LR, right? This is learning rate, and this number is usually very small, and you might have to experiment with this number to figure out which is the best possible number for this learning rate, so that your gradient descent algorithm works well, right? So this is our update for WR, right? So just to recap, this derivative term actually gave you a direction of whether or not you want to decrease the value of W or increase the value of W, right? Do you want to go up the graph, or do you want to go down the graph, right? In this case, since the slope is positive, this indicates that if I nudge the value of W just a bit in the positive direction, the value of J is influenced as well, but it is influenced as increasing the value of J, right? It is being influenced by being increased. So what you want to do is to decrease the value of W. So we can see that this formula works even if we start it at this position, right? At this position, we know that the tangent line is like that, right? And if I draw a triangle, if I nudge W in a positive direction, I'm actually going down. So the slope is negative. We don't want to know, it's not necessarily needed to know the exact value of the slope, but we know that the value, whatever the value might be, it's a negative number, right? So that means that if I nudge W in a positive direction, the value of J is actually decreasing, which is exactly what we want. So the derivative here would be a negative number. So this thing right here would be a negative number, right? And we want WR to be increased, right? Since this is a negative number, this whole thing is a negative number. This is always a positive number, this alpha. A negative number times alpha would be a negative number, but you also have this negative number. So this comes out to be a positive number, right? And then you're adding that whole positive number to WR. So what ends up happening is that you're increasing the value of WR, which is exactly what we want to reach the global minima, right? So that's what gradient descent does. In summary, gradient descent is an algorithm. So gradient descent, I'll just write GD for LR, right, is repeat, right? That is to say, until you have converged. And I should talk about what do we mean by convergence. What we mean is that if we are at the minima, right, let's say you are, after some updates, you reached to WI. Let's say WR is now equal to WI, the optimal value that we wanted to reach, right? In that case, the slope here would be 0. And if the slope is 0, this term becomes 0. You multiply any number with 0, that is 0. So you end up not updating WR at all, right? So you have converged, right? So you have to repeat this process, this whole process, until convergence. So I'm going to write W, assign W, um, W minus alpha, the derivative of J, right? And let's assume that this is Wj, right? And this could be any number of parameters, right? So this is general with respect to Wj, right? And you also want to update the value of b simultaneously, right? With respect to b, right? So this is our gradient descent. This whole thing is our gradient descent. And that's what gradient descent is. It's very simple, but very effective. So one last thing that you might be wondering is that how do we compute these derivatives? Because once we have these derivatives, everything becomes easy, right? So that's kind of going up in a bit detail for because we require calculus to actually compute the derivative uh, of this expression with respect to w and b, which I can do very quickly. Okay, so if you know a bit about calculus, you would be immediately able to actually derive these derivatives uh, using chain rule, right? So given these, right, now we can actually compute uh, the, or rather, now we can compute the derivatives in our code because now we have the derivative expressions, right? So if I want to expand this out a bit, so this is actually the gradient descent that we'll be implementing in the next video. Thank you very much for watching. See you next time.